have what I hope is a familiar definition written on the top of the board. The set of all points in R2, the plane, that are equidistant from a fixed point is a circle. So when I'm thinking about R2, if I fix a point, and then I imagine taking all of the points that are the same distance away from that given point, I end up getting a circle. And I can imagine taking this distance, which I'll call R, spinning it around that circle and tracing out my circle. We'll pretend that's a circle. And in fact, given some information about where the center lives, we can even use the distance equation to derive this, the standard equation of a circle, centered at h comma k with a radius of r. Well, I want to take this very familiar definition and just imagine changing R2 to R3 and then seeing what I get. So I'm going to imagine two blanks there, and when the first blank was filled in with R2, the second blank was filled in with the word circle. So let's play a little game. Let's change that first blank to saying R3. And let's change that second blank to saying, well, I'll tell you what, write down for now what you think the answer is, and then we'll go from there. So I take a right-handed coordinate system in R3 and I imagine plotting a center somewhere, and then I go out a fixed distance, and I imagine I could spin that around in any direction I want in a whole lot of circles, and I hope that you wrote down that you would get a sphere. That, if I take this point that's right in the middle of the sphere and measure distance to anywhere on here, I always get the same distance. Another way to think about that is imagine taking your circle and spinning it around its own center through a third dimension that somehow we now magically have access to. So, I get a sphere. Well, let's imagine the center of that sphere is at x naught, y naught, z naught. Instead of using h's and k's and then some other letter, let's just say x naught, y naught, z naught. That's that point right in the middle. Well, if I go back and think about my distance equation, if I called the radius of that sphere r, right, that amount that we're away from the center, that equal distance every point is away, I could satisfy that three-dimensional distance formula we derived in our last video, and I'd say, well, for any point x, y, z on the surface of that sphere, this equation would have to be true. Please pretend that's still under my square root symbol. I kind of ran out of room. And so now I could imagine just squaring both sides of that equation, and I get what we'll know as the standard equation of a sphere centered at x naught, y naught, z naught with a radius of r. So I get x minus x naught squared plus y minus y naught squared plus z minus z naught squared equals r squared. And again, if I cover up the z part, I have the equation of a circle. Well, that's nice. They come from the same definition. And if I think back to my pre-calculus class, the equation of the circle in the plane also comes from the distance equation. So again, we have an example of something that generalizes nicely from R2 to R3. But I left some space over here, so now I want to think about what would happen if I replace R3 instead of with R2 with R1. And think about what we would fill that second blank in with. So I'm looking for all of the points on a number line, R1, that are equidistant from a fixed point, which we could just call x naught. Well, if I'm allowed to go a distance r away on that number line, I'd get a point over here, and I'd get a point over here, right? That pair of points, and I guess that's what I can write here, a pair of points. Is really all I get on that number line. Okay, well, let's think about being one of these 2 points. It doesn't matter which one, let's just call it x, right? Because x could be this one or x could be that one. Well, what I could tell you is that the square root of x minus x naught squared is equal to r, which means x minus x naught squared is equal to r squared. Right, because that was that kind of unusual notion of distance we wrote down for between 2 points on a number line, but what I see now are 3 equations that generalize nicely from the same definition, just playing around with whether I'm in R1, R2, or R3. And for that reason, we kind of think of these as the same thing, or mathematically you'll find people that think of these as the same kind of object. We're used to calling this one a sphere. To a mathematician, we would call this the 2-sphere. And call it S and then put the 2 in a superscript position in the exponent. And the reason for that is if I think about the outside of a sphere, it has area, so it on the outside looks like R2, right? It has area, so we call that S2. Colloquially, we call this a circle, but if we were going to name it, we'd call it the 1-sphere, S1. Because if I wanted to measure around it, I'd get a length, right? It behaves like R1. And then my pair of points here, we would call the 0-sphere. So, by adjusting this definition, we have 3 different ideas of sphere. And in this class, we don't actually have to call these things spheres. I'll continue to call this one a circle and this one a sphere, but I might use this symbol to represent it, right? S2. And maybe if we deal with a circle, I'll call it an S1. But really, we just need this notion of the equation of a sphere. But it's always nice to see what happens as we generalize from R1 to R2 to R3.